All right, so today we will discuss module 10. So this is our second last module in which I will talk about the non-ferrous metal. So we end our discussion on the ferrous metal last week. In the last week module 9, we talked about plain carbon steel and also the alloy steel. When we add more alloying element, different alloying element rather than just carbon, we classify the material, the alloy, as alloyed steel. So today we're going to look into non-ferrous metal. So this basically we're going to talk more on the applications of the non-ferrous metal. The one that I will discuss today is the aluminum and copper alloy. So we will see how the properties of the materials relates to its crystal structure and how the microstructure formation will result in a type of alloy that we can heat treat it or the one that we cannot heat treat it. So that's what we're going to look into today. So I'm going to share my slide. There are a few videos that I would like to share with you guys today. So today we're just basically going to have fun, look into the application, where they're being used, and also the production of aluminum and copper itself. So it's not a very difficult topic to understand. And for final exam, you basically are going to be asked about the applications of this. For the homework number 3 that I gave you also involved this type of alloy, copper alloy and also aluminum alloy, and how you can, maybe you have already been doing your own research and which of these application, this alloy used in which application. All right, so that's what we're going to look into today. So this is lesson 1 for module 10. We will focus our attention of aluminum and copper alloy. So the learning outcome for today is for us to be able to describe the general properties of aluminum alloy and also the general properties of copper alloy. And we are going to be able to explain the heat treatment process that involve in strengthening aluminum and copper alloy. So can someone please repost the link for Prem? Thanks, Isa. Okay, so that's what we're going to look into, the heat treatment process that we call as age hardening. So that's another learning outcome. And finally, we are going to look into the various application of aluminum and copper alloy. All right, so as I have explained in the previous lecture, we can classify metal into 2 classifications, which is ferrous and non-ferrous. So we have finished our discussion on the ferrous metal. So ferrous metal is when the host materials is iron. So those alloy with the alloying element, iron as the alloying element, we call them as ferrous alloy. And when we have the alloying, the host materials is other than iron, we call this as non-ferrous alloy. So we have used a lot of non-ferrous alloy in a lot of engineering application. We want to have a look at how it behaves, its mechanical behavior, and where they are generally being used and why they are used in those kind of application. All right, so when we define a metal as non-ferrous metal, as I said, it means that it does not have a significant amount of iron in its chemical composition. So here, if we add iron is actually the alloying element. So it is not the host materials for this alloy. So aluminum alloy itself can be classified into 3 classifications, which is cast and wrought aluminum alloy. And also in this cast and the wrought aluminum alloy, they can be classified into the one we can heat treat and the one that we cannot heat treat. So another for copper alloy, so I will emphasize on aluminum and copper in this lecture because they are the most commonly used non-ferrous metal in engineering application. And for copper, we also have cast and wrought alloy, and they also can be heat treated, and some of them are non-heat treatable. And next week, we're going to look into the other types of non-ferrous metals, such as magnesium, titanium, and nickel. Not that they're not important, but they are as important. A lot of other applications in engineering use these materials. But today, we're just going to focus on these two types of alloy, which is aluminum and copper alloy. So for the classification that we classify as cast alloy, this means that this alloy, in order for us to fabricate the final shape, it needs to undergo casting process. So the alloy needs to be melted and then poured into the mold and allowed to cool to its final shape into that alloy, into that final shape, into that mold. So the reason why they need to be shaped in this method is because we put a lot of percentage of alloying element. So it means that the alloy becomes brittle. So when they are brittle, what's going to happen? The same as cast iron as well, is that we cannot shape them through machining. We cannot shape them through plastic deformation. So if we have semi-product and we want to shape them to final product, it cannot go through that process because it will break when we apply force that's going to cause them to deform plastically. So this is the classification and the definition of cast alloy. And for the wrought alloy is when the alloy is worked in the solid form to have its final shape. So they can be stamped, bent, roll, extrude into their final shape. And obviously we need to use specific tools to have this final product, the shape of that final product through plastic deformation process. So these two manufacturing processes will yield two materials with very different properties. So we can have aluminum alloy that have both, for example, copper and also as an alloying element, but one composition has a small number of copper and the other one has a large number of copper. So we need to process them differently into their final shape because the one with the larger number of copper will become brittle compared to the one with the smaller number of alloying element. So why is this? And we can go back to our module 6 again. If we look into module 6, when we have a smaller number, especially for like copper and aluminum, when we have a smaller number of copper inside aluminum, it can form a complete solid solution. So we will have just one phase. But when we have a lot more of copper, the other phase will start to precipitate as well. So we will have final product that consists different microstructure. So this will make the materials brittle. So if we want to shape them, they need to go into different process. So those are the difference between the cast alloy and the wrought alloy. And also for aluminum alloy and also copper alloy, we can heat treat them through a heat treatment process that we call as precipitation hardening. So this heat treatment process is for non-ferrous metal in which the final product will have small precipitation of other phases distributed evenly in the microstructure. So certain alloy with certain aluminum alloy especially aluminum copper alloy with certain composition can go through this heat treatment process. So precipitation hardening, or sometimes they call as edge hardening. So they both are the same process. So precipitation hardening is a heat treatment process used to increase the strength of many aluminum alloy and also other metal alloy. So the objective of precipitation hardening is to create a heat-treated alloy with a dense and fine dispersion of precipitates particle in a matrix of aluminum, metal aluminum or copper. So as you have learned in module 4, strengthening mechanism of materials. If we have small precipitates distributed evenly in the microstructure of an alloy, what's going to happen, that precipitate will be the location where the dislocation motion will be impinged or will be obstructed. So if we can introduce these precipitates throughout the microstructure of the aluminum or copper, we can strengthen its this alloy. So we can have higher yield strength, and also we will have a better, a higher Young's modulus. So the materials will become stiffer. So that's the heat treatment process. So now let's have a look on what composition of alloy that can be heat treated. So if I will use this example of aluminum copper as the example in explaining the this heat treatment, the precipitation hardening. So you look at this phase diagram. So this phase diagram belongs to aluminum and copper. So I have given this in your homework. I hope everyone did not find this and something new. So I assume that most of you have submitted your homework. I can see actually in my class 35, but during the initial submission, there's only 33 people only submit this. But also this morning when I check again, there's only 27. So the submission, some of the submission went missing, and I know it went missing, but I need to retrieve this from the library. So what I need you to do to recheck your submission. If it's not there, you have to let me know so I can tell the library, or I can accept submission outside the Turnitin. But for your test, you need to tell me if it's not there. So I have a few students that already text me, but there are still some that has not text me because you did not check yet. So please check it. For the assignment, I can see a few. There's your name is there, but your file isn't there. For example, Iza did not have her file, and also Prem did not have your file in there. Your submission went missing. So please have a look. What's happened there? Have you changed your email or not? And let me know. Okay. I'm not accusing that you did not submit. I just want to know. And if you cannot see it, please submit it again, but you can submit to me privately in WhatsApp or email. Okay, so that's enough of that announcement. Go back to this heat treatment process that we call precipitation hardening. So if you look at the aluminum copper here, aluminum copper alloy means that the aluminum is the main host materials, with some copper being added as alloying element. So not all copper, not all of this aluminum alloy can be heat treated. The one that can be heat treated is the one that is in this composition that you can see before that eutectic composition line. So before that eutectic line. So with a maximum of around that, which is about 5 or 6% of copper, this aluminum alloy can be heat treated. So how do we do that? Let's have a look and do some revision on the microstructure when this alloy with this composition solidify. So I will enhance that side of that, zoom in that side of that phase diagram, and we look into this alloy that initially have solidified to become alpha phase, become alpha aluminum. Okay, so I will take an example of aluminum at 4% of copper. So when it's solidified, once it reached that point there, alpha solid solution will start to precipitate. And at this point here, we will have alpha and liquid phase. So the first microstructure will be alpha, and it will become bigger and bigger and bigger. And as soon as it reaches that solidus line, so at that solidus line and below that solidus line, we only have alpha solid solution. So you can see that all of this microstructure throughout this whole volume will be alpha. Will be alpha, 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 and alpha. So this is also alpha, and the rest is liquid. All right. So I hope no one find this a new thing. This is what we have learned in module 6. And when this is all solid at that point, but you look when it touched that line, that copper will become super saturated in that alpha phase. So alpha will be the copper will start to precipitate out after it reaches that point. So when it's reduced, the temperature reduced, we can see this is a solvus line. So that's a solvus line. And we can see that the crystal structure will start to shrink and shrink and shrink. So the copper will be precipitates out as the temperature, more and more copper will be precipitates out at the grain boundary as the temperature drops. But copper will not be precipitated out just by itself. Some of the aluminum will precipitate out as well. So we will have beta, or in this case is theta. Okay, so we will have another compound that will be precipitates out at that. So we have alpha, 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 alpha. And at the grain boundary, we have theta solid solution. So this is what happened as the temperature drops. But this will strengthen the mechanical behavior of the materials, but it's not going to make a very huge difference, because this is also a precipitate. So what's going to happen is that we will have precipitation hardening. But if we want to strengthen these materials even more, we can heat treat them. So if we have the final microstructure as the one that you see here, we can actually heat treat them. So how does we perform this heat treatment process? So what's going to happen is that we need to heat up these materials again, this microstructure. So this is the microstructure that I draw just then with alpha as the matrix. And this is theta. So this is microstructure after an equilibrium solidification process, when we cool it down slowly. So this is what we have. So what's going to happen when we perform this heat treatment process is that we're going to heat it up again, so that all the copper is gonna go back to that alpha solid solution. So we are needing to increase the temperature to a temperature where alpha will exist again. So that's what we are going to do. So we're going to heat it up to a temperature of around 548 degrees Celsius, and we're going to let it sit at that temperature for a period of time. So we will have, after this solution treatment process, this is where we soak them at that temperature, we call it as solution treatment process. So after this solution treatment process, only alpha solution will exist again, because when we increase the temperature, copper can go back to alpha solid solution. So this is what we are going to have. This microstructure consists only alpha, 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 alpha. So what if we quench them? So if we quench this microstructure for inside the water, for example, we reduce the temperature rapidly. That precipitation cannot happen. So copper cannot be squeezed out. It does not have time to diffuse or precipitate out of that alpha solid solution. So this microstructure will be retained at room temperature. So this microstructure will be like that at this room temperature. But this microstructure is metastable. This is what we call as a metastable microstructure. Means that it is not stable in that phase. We know that copper is supersaturated inside alpha. It wants to go out. So what we can do, we can exploit that properties, and we can increase the temperature slightly above, not to make it, not to heat it up to a temperature as high as 548 again. We can heat it up to a temperature at around 200, for example. Okay, at that temperature, a short range diffusions of atom can happen. So this is at a lower temperature, but Irsyad, boleh tolong mute? Okay. So, sekejap, saya mute dulu. Mana Irsyad ni? Okay. All right. So as I continue on, as I said just then, what will happen is that if we increase the temperature just slightly above, so it's around 100, 200. So we know that diffusions of atom needs to be activated at a higher temperature. But if it's not too high, small range diffusion can still happen. So the atoms of copper can still diffuse out and create the other precipitates throughout this matrix through short range diffusion, because the temperature is not as high as the long range diffusion can happen. So only a short range can happen. So if we hold it for this temperature that is lower than that 548, what can happen? All this theta phase can start to precipitate out of the matrix of this alpha phase. So the final microstructure, when all of these precipitates comes out at the matrix of this grain of the alpha, we will see that these materials, if we do the hardness test, we will see that it has a better hardness and also high strength. Because again, these small precipitates will be effective in stopping the plastic deformation from happening. It will stop the dislocations from moving, and therefore it will require a higher strength for us in order for us to want to move them. So this fine dispersion of precipitate within the grain will be retained upon cooling as well. So that's what's going to happen to this material during this precipitation or the age hardening. All right, so this precipitation hardening is actually discovered by Wilfred Wilm. He's an engineer in 1903. So he is an engineer in German. So he was studying, he was doing a research on copper, aluminum copper alloy, and he wants to do heat treatment that is similar to when we form martensite in steel. So how do we form martensite in steel? We quench it to room temperature. So when he quenched it to room temperature, from higher temperature to room temperature, he found out that the strength did not improve, the hardness did not improve. Strength improved, but the hardness did not improve. So the materials actually still soft. So he becomes really frustrated. So at the last time before he actually discovered this process, what happened was that he did that quenching process. It was on Saturday morning. So in Saturday morning, his lab assistant did a hardness test, but he did not complete that hardness test because they have to close the lab because it's a weekend. So on Sunday, they actually leave that specimen that has already been quenched in the lab. But it was summer and it was a sunny day during the Sunday, so the lab environment is a little bit hotter. So what happened was that when he come back on Monday, after he leave that specimen in that lab for 24 plus hours, and he did that, he continued with that hardness test, and he discovered that actually that hardness increased significantly. So that is when they discover that if they leave it at a higher temperature, but not too high, that it will allow that metastable phase to become stable by creating these short-range precipitates all over the matrix. So it is heat treatment process is actually discovered by accident. So then they keep on doing that hardness test for a few days, and only after 4 days that the hardness increase until the 4th day it becomes constant. So what does that mean is that all these copper atoms that cannot reside in alpha has already become precipitates in the matrix of that matrix of that alloy. So that's what happened. So if you want to look at the mechanism of this precipitation hardening, as I've mentioned, the alloying element, we can imagine that this alloying element, the host materials is aluminum. As I said, that we've learned that aluminum has FCC crystal structure. So what's going to happen when we add copper? So copper will reside in the crystal structure, in that alpha solid solution. Copper will reside in the crystal structure of aluminum. But because copper has a larger size, it will distort the crystal lattice of the host materials. So only certain percentage can reside in the crystal structure. So when the temperature drops, this distortions become higher distortion, because the atoms starts to getting closer and closer to each other. So eventually this copper will precipitate out to the grain boundary. So what happened when we quench them to a room temperature? It cannot do that. So it becomes solid solution, but it's still in the crystal structure of alpha, in the crystal structure of aluminum, but it is not stable in there. So what's going to happen if we increase the temperature slightly? They will start to accumulate with one another that is closer to them. and form the compound. Here the compound is Al2Cu, if I'm not mistaken. So let's, yeah, CuAl2. Yeah. So that's the compound. So that's what happened here. So the one that's closer to each other will start to coalesce with the other and form that precipitates, and that precipitates reside in the grain of the alpha phase. So that's what the age hardening did to this copper that trapped inside that crystal structure. So this is the process of precipitation hardening. So we will have a lot of these precipitates throughout that matrix. So this is how the heat treatment process of non-ferrous metal being done. So if we look at the microstructure, the real microstructure, so this is the equilibrium microstructure before we perform precipitation hardening. You can see that the matrix here is the alpha solid solution with the theta solid solution on the grain boundary of these materials. And then when we perform the precipitation hardening, you can see that the fine dispersion of theta can be distributed uniformly in that in the grain of alpha solid solution. So it will become more effective to prevent or to stop the dislocation motion. There are some limitation as well for this process. So for this process, if we overage them, the precipitates can become bigger, and that will reduce its efficiency to harden the materials. And also we can make the if we did not age them enough, we will also have the effect of underage. So we will have a very small and underdeveloped precipitates. So if precipitation process is continuous for so long, the precipitates will have opportunity to become bigger. So that's grain growth. We learned that in lab module 4 as well. So we'll allow more atoms to diffuse, so the precipitates will become bigger, and it will be less effective as dislocation barrier. All right, so that's how the heat treatment process of aluminum and copper is being done. So now we can move on to look into the aluminum alloy. What is aluminum alloy is all about? So before we start with that, I have this video that I want to show how aluminum is being extracted from its core. So let's have a look at that. Let me know if you can hear the sound, yeah? Boleh dengar?
Ya, dengar dulu.
Oh, okay, all right. So this tells how aluminum being extracted. So that is a video from Emirates Global Aluminium. It is one of the world's largest premium aluminium producer. So I hope you learned something on how the aluminium is being extracted. So the ore for this aluminium is bauxite, and it's being normally it's being mined in a tropical country. And from there, it's being processed, and the final product will be about pure aluminum. And only when we have that pure aluminum that we can add with different alloying element to produce aluminum alloy with a different mechanical behavior. And also some of it is to improve its chemical reaction, its corrosion properties and all that. All right, so the general properties of aluminum, of unalloyed aluminum. So when aluminum exists in its pure condition, also when you look into that materials processing, how they come up with the aluminum metal, it's very extensive. The process is very, it requires a lot of steps. That's why, and when we have a look at copper alloy, I will show you another video also how copper alloy is being extracted. You can also see why this alloy is expensive because of their processing. Even though aluminum is bauxite is one of the most abundant materials, but because of this process makes them quite expensive if we compare to steel, to iron-based metal. All right, so some of the general properties of aluminum that has not been alloyed yet is that it has a very low density. So aluminum is very light. So that's why we use them a lot as a food packaging and also for a lot of aircraft parts, especially for the body of the materials of the aircraft, we use aluminum because it has a very low density. So it is much lighter if we compare to steel. Another properties is that it has excellent resistance to corrosion due to its tendency to form oxide on its layer, outer layer. So this is the scanning electron microscope image of aluminum with the oxide layer formed on top of it. So the base aluminum here is aluminum alloy. And what happened is that when it's being exposed to oxygen, to the environment, these aluminum atoms can combine with the oxygen to form an oxide layer on the surface. So that is why it has a very good corrosion resistance. This oxide layer will protect the underlying materials, the base alloy, aluminum alloy. So that's why aluminum did not have that rust that you can see in iron. So that rust is actually a layer as well. When iron react with oxygen, it will form that rust. So it has that similar concept as well. So this layer will protect aluminum on the base. Another properties is that it has 3 valence electron. Since there are only few electrons that are available for the metallic bonding, the pure metal is soft and it also have low melting point. So apart from that, aluminum is non-magnetic and it's also have it is very ductile. So if you have aluminum strip, you can actually bend them to any form easily without too much effort. So this is because the crystal structure of aluminum is FCC. FCC have has 12 slip system, and this will allow the dislocations to move freely. When it's being activated, dislocation has 12 system in order for it to move. So to overcome, so the ductility can be a limitation because if we want a stronger materials, we need the materials to have higher strength and hardness. So we can overcome this ductility by strengthening this mechanism through alloying element. So we can add copper, as you can see just then, we can add copper to improve its strength and hardness. We can also add magnesium. There are there are aluminum that we can add silicon and manganese and zinc, and it will create an alloy with different properties. So the application for the unalloyed aluminum without any alloying element. So one of the major application for this unalloyed aluminum is as electrical wire. So since it has only 3 valence, aluminum has excellent electrical conductivity. So that's the same with copper as well. So copper has a better conductivity, but aluminum is not too bad either. So with as we know that the release of the aluminum ion, the release of the electrons from its the release of electrons from the outermost shell is depend on the energy that we need. It depends on the number of that valence electron. So when the number is lower and lower, it's easier for these electrons to be free from that shell. So when we have only 3, it will be easily for these electrons to be free from its shell. So what will happen? What happened with aluminum is that it has, because of this, it has a good electrical conductivity. So aluminum has 61% the conductivity of copper, but aluminum is very light. So compared to copper, aluminum is a lighter metal. So it has 30% of the weight, has only 30% of the weight of copper. So due to this, there have been used to transmit electricity for a long time now. Aluminum wire has been used in high voltage transmission. So that is the application, one of the application of unalloyed aluminum. So as I mentioned earlier on, aluminum can be classified into 2, which is cast aluminum and also wrought aluminum. So for wrought aluminum alloy, the primary fabrication is through machining and also through plastic deformation. So it's the semi-finished product is in the shape of sheet, ingot, rod, and billet, as what you can see in the video I show you just then. So that's the finished product. So when we want to shape them into its final product, we need to roll them, we need to extrude them to its final product. Aluminum alloy produced in the wrought form are classified according to its major alloying element. So you probably have seen the series of aluminum alloy. So with the 1000 series, when we saw the label and it shows that it's 1000 series aluminum, this means that this aluminum is almost pure, almost 99% of the content of that metal is aluminum. And if we have the 2000 series, the 2000 series means that the major alloying element is copper. For the 3000 series, the major alloying element is manganese. 4000 series silicon, 5000 series is the magnesium. And if we have the alloying element, the major alloying element is magnesium and silicon, they are classified as the 6000 series. And with zinc as the major alloying element, we denote them as the 7000 series, and we have all the others. If we have other alloying element, they are all classified into the 8000 series. So that's for the wrought aluminum alloy. So let's have a look at the this series, where they've been used and what are the properties of all these different series. So for the commercially pure aluminum, the one with almost 100% of aluminum, so when we classify them as a 1000 series, or 99% of this alloy contain aluminum, and with only 1% or less than 1% as the other impurity. So with this alloying element, they are very excellent in terms of their corrosion resistance, their formability, the ability to be shaped into different shape. They have good height, they have high thermal and excellent conductivity because of that valence electron. And also this series is commonly used, as I have mentioned just then, as power lines. And most of the power lines that connect the national grids across Peninsular Malaysia use aluminum wire to transmit the electrical power. So the 1100 series used as a food packaging. So what's the difference between the 1100 and the 1100 series and the 1350 series is that the amount of aluminum for the 1350 is 99.5. For the 1100, the impurity is 1%. So that's the only difference between them. So they are almost pure. All right, so that's for the commercially pure aluminum, which is the 1000 series. If you guys have any questions, just put it in the chat box and I will entertain them when I have time. All right, so and then we have wrought alloy that can be heat treated and that cannot be heat treated. So we will begin with the series that can be heat treated first. So the 2000 series, the 6000 series, and also the 7000 series can be heat treated. To a certain composition, it can be heat treated. So for the 2000 series, in which the major aluminium element is copper, these materials, this alloy can be heat treated as I have shown you in the previous slides. We can do precipitation hardening if we have the amount of copper up to a certain percentage. So this alloy possess high strength and toughness, but due to low level of atmospheric corrosion resistance, they are generally clad with the other series, which is the 6000 series. So this I have asked you in the questions. When we add copper in aluminum, stress corrosion cracking can happen. So these materials is not good in corrosion resistance. It still can sustain corrosion, but up to a certain percentage. So that's what happened here. So because of that, normally there will be layered with the other types of aluminum alloy, which is the 6000 series. And some of the major applications of this alloy is as the aircraft alloy. They've been used for the body of aircraft. So just a little bit of fun fact here. The Wright brothers is the first one that used the crankshaft the crankcase aluminum crankcase for their engine, for their aircraft engine. So the Wright engine with the aluminum crankcase marked the first time the aluminum alloy was used in aircraft construction. So this happened in 1903. The lightweight aluminum became essential in the aircraft design and development and remains the primary construction materials for all type of aircraft. So what happened was that when the Wright brothers, once they have decided that they will have a powered flight, so they did the calculation and mathematically they need materials that the engine that has the 8 horsepower, but with only 91 kilograms. So the weight need to be as light as possible. So this is what their calculation tell them. And the usual cast iron metal is going to be very, very, very heavy. So they need to use other metal. So what they did is that they learned that Mercedes-Benz at that point already make an engine with aluminum, copper or aluminum, something like that, but with non-ferrous metal. So they try to cast this crankcase using aluminum. So that's what they did. But this is really in a secret. So what they did was that they painted in black, so people don't know that they are using it. They're using aluminum as this crankcase for their engine. So that's what happened. And this engine actually, the crankcase has a composition of 92% aluminum with 8% of copper. So that was the first time aluminum alloy is being used in the aircraft construction. So that's for the 2000 series, and then we also have the 6000 series. So the 6000 series has aluminum, has silicon and magnesium, as the major alloying element, and this will make the materials to have the very excellent corrosion resistant. So it is versatile, it can be heat treated, and it's also have high formability and has moderate strength coupled with excellent corrosion resistance. So the main reason is to improve the corrosion resistance. So the extrusion product of the 6000 series are first choice for architectural and also for structural application. So they've been used, also the 6061 has been used as the automotive parts, and the iPhone, also Apple used this series for their aluminum case. So those are some of the application for this alloy. So you can, if you are interested, you can Google about it. The 7000 series with zinc as the major alloying element, also heat treatable, and they have a small amount of magnesium, copper, and chromium inside this metal as well. So they have high strength and they are heat treatable, and they've been used throughout the aircraft industry. So the 7075 is used as a structural part of the aircraft as well. So the Apple Watch, the casing for the Apple Watch is also using this type of alloy. So when Apple Watch was introduced in 2015 by Apple, the aluminum is actually trademarked to them. So they must have a secret recipe to make that aluminum alloy. But it is in the 7000 series with the zinc as the main alloying element. All right, so some of the, as you can see for the A380, so this is the A380 aircraft. So as you can see here, a lot of aluminium has been used in the construction of this aircraft. You can see aluminum lithium is used as the floor structure of this aluminum of this aircraft. The aluminum with 6000 series is used as the lower fuselage. Glare is another type of composite. So it's a composite material of glass fiber in the middle with aluminum sandwich, with that glass fiber sandwich in between two sheets of aluminum. So we call this material as glare. But the sheets of aluminum that they use to sandwich this glass fiber is from the 2024 series. You can also, that the wings is made of aluminum as well. So this is the major reason why aluminum is being used is the lightweight. So we need to reduce the light as much as possible for energy efficiency, for us to have more paying load. Instead of carrying the body weight of that aircraft, we can carry a lot more people and the paying load. So they have used a lot of aluminum in this kind of application. All right, now we go to the non-heat treatable wrought aluminum alloy. So this is still in the classification of wrought aluminum, but it's non-heat treatable. So the 3000 series with a small amount of manganese as the alloying element and magnesium is non-heat treatable. So there's this series are generally used serve as general purpose alloy because it has moderate strength and good workability. So they can be cold in order for us to strengthen them. Remember the strengthening mechanism of metal. One of it is to induce strain hardening. So if we want to strengthen this metal, instead of heat treatment, we need to do strain hardening. So we need to introduce cold working. The example of application is as heat exchanger, and also the case for the soda can, Coca-Cola, they all are from this series. Can we have a 5-minute break? I need to drink some water. So be back in 5 minutes, okay?
Yeah, okay.
All right, guys, it's me again. All right, so now we have a look at the other non-heat treatable aluminum alloy, which is the 4000 series. So the 4000 series has a silicon as the major alloying element, and it is added to lower the melting point without affecting the brittleness. So this is the effect of the silicon when we add them into the 4000 series. So it is excellent as a welding wire and brazing alloy, where the lower melting point is required. So when we're needing them to be used as the welding wire or a soldering alloy, it needs to be at a lower temperature. So easy for us to work with them. And it is widely used as a filter alloy in a structural and automotive application. So they can be cold work. In order for us to increase its strength, we need to cold work them. So the 4043 aluminum filler is used as aluminum filler wire. So that's the 4000 series, and the last one in the non-heat treatable is the 5000 series. So the 5000 series has magnesium as the major alloying element. So this alloy has a moderate to high strength. It has good weldability and also good resistance to marine environment. So they're widely used in building and construction and storage tank. So the core work is induced also through strain hardening. The strengthening of the mechanism, strengthening mechanism is through strain hardening or core working. So they've been used in a lot of applications. One example is the 5083 series is used as the body for the armor vehicle. They've been used in a lot of marine application because of the good corrosion resistance in the marine environment. So that's where they have been used. And if we have a look at the other classification with the casting, so the casting alloy, the aluminum that is classified as the cast aluminum, offers another advantages. So the aluminum casting alloy offer a range of advantages, particularly with the ability to be cast properly. So this is because this aluminum alloy have high fluidity, so it's easy for us to pour them. They're easy to flow inside the cast, so that will give a final product with a good dimension. So it also have low melting point, relatively low tendency for hot cracking, and they have good surface finish and chemical stability. So they can also be classified into different groups based on their alloying element. So the 100 series is the almost pure aluminum that we cast them into its final product. So they basically is the same as the one that we've seen before, I've discussed before. The 1000 series has 99% of aluminum. This 100 series also has 99% aluminum. What differentiates them is the way we shape them into the final product. And for the 2000 series and the 200 series, they also have the same copper as the alloying element. But here, the amount of copper is much higher. So it's not possible for us to shape them into its final product through machining. So instead, we need to cast them. So the only difference between them is that one can be shaped through machining. The other one, because of the higher percentage of alloying element, they need to be cast. So here I've listed out the different properties and application of the heat-treatable aluminum alloy. So the one with the 200 series, 300 series, and the 700 series are all heat-treatable. So you can read if you are interested. You can find out where they've been used. So I have listed out the properties as well. And for the non-heat-treatable, the description, the properties, and the application is in this table here. So as you can see, for the aluminum with the silicon as the major alloying element, for this cast aluminum alloy, it means that the amount of the silicon is much higher. All right, so that's for aluminum, and we have the new generation of aluminum alloy. So the new generation of aluminum alloy is one of it is the aluminum lithium alloy. So with this alloy, the alloying element is lithium. So lithium is the lightest metal found in nature. So with aluminum that is already quite light, it's have a very low density. If we can add another element that is lighter than that. So what's going to happen is that we can increase its strength by this addition of this alloying element, and at the same time we can reduce its weight. So the lithium addition will increase the strength and modulus of that aluminum, but also at the same time it will also lower the density. So the propellant tank of the Falcon 9 are made of aluminum lithium alloy. So SpaceX actually named this rocket, their rocket, after the Millennium Falcon. So they use the name Aluminum Falcon. So this is just to follow what's the Millennium Falcon in the Star Wars series. So the second, the high strength aluminum lithium alloy is used here in the Falcon 9, the tank wall for the SpaceX Falcon 9. All right, another application where they have used aluminum lithium is the frame structure, as what I showed you just then, in the A380 A-bus as well. So that's where this aluminum is being used. So the properties of lithium is being exploited by the addition, by adding them into aluminum. So we can increase the strength modulus at the same time, reduce the density. All right, so here I have listed some of the effect of the alloying element, even though I've already explained in each of the slides. So silicon here reduce the melting temperature and improve the fluidity. As if we add zinc with magnesium and copper, it produces heat-treatable alloy with high strength. And also if we add manganese, we can increase the strength of the materials. So that's all for the aluminum. Now we can have a look at the copper alloy. So before I start with the copper alloy, anyone wants to ask me a question? Kalau tak ada soalan.
Doctor.
Yep.
Actually, in the homework 3, we do have the last question about asking introduction the copper into the aluminum alloy can reduce the corrosion resistant aluminum, right? So actually, I still confusing on how the copper into the aluminum alloy enter the aluminum alloy that can reduce the corrosion resistant aluminum, because if we have the aluminum bronze alloy, then it should be have form the aluminum should have form outside layer and protect the inside one, right? But when the copper into the aluminum alloy, how it can?
So that is another topic. If you study the corrosion, you will look into this a little bit more. But the type of corrosion that is going to be caused by introduction of copper into aluminum is the one that I said just then, is stress corrosion cracking. So that is quite a lot. I've covered that when I first teach this subject. But what I want you to do in that homework is actually do your own research. But since you asked, when I discuss about that homework, once I finish marking all of them, I will explain to you how it happened. Okay?
Okay, thank you, Doctor.
All right, no problem. So that's the difference. When we introduce copper into aluminum, it actually induces stress corrosion cracking. But when we introduce aluminum, as what you said, into copper, it's actually improved the copper corrosion resistant. So when I discuss, hopefully I can finish marking all of them by this week, so we can look into it before your test to start. So you have any idea on how to answer those kind of questions. So fingers crossed, hopefully we can get into that homework, those 2 homeworks that I gave you, by next week. All right, so for copper, I would like to show you this video where we will have a look at the production of copper as well. So at least you have an idea on how this the copper metal, the pure copper metal, is being produced. So let's have a look. Also, let me know if you can hear the sound.
Have you ever wondered? Have you ever wondered what your life would be like without copper? Don't worry, it's not something most people spend a lot of time thinking about. But the fact is that without this basic element, you'd be stuck with no running water, no phone, no computer, and no electricity for that matter. In other words, without copper, your life would be downright primitive. So now that you know how important copper is, let's talk about how it's made. Or to be more accurate, let's talk about how it goes from this, a basic element mixed in with a bunch of other minerals and garden variety rock, to this, 99.99% pure copper cathodes manufacturers use to make that long list of stuff you depend on every day. The whole process starts with monster machines and high explosives. At the Bingham Canyon mine, teams of blasting experts drill 12-inch diameter holes 56 feet into solid rock, fill the holes with about 1,200 pounds of high explosives, and boom! Solid rock instantly becomes loose rock. In fact, every single day, blasting crews drill and blast about 160 of these holes to create 500,000 tons of new blasted ore. So exactly how much is 500,000 tons? Well, a humpback whale, one of the world's largest animals, weighs about 50 tons, which means you'd need about 10,000 of them to balance the scales. So how does Kennecott deal with this nearly inconceivable volume of blasted rock? Well, the simple answer is that you pick it up with giant shovels that can carry 100 tons in a single scoop and dump it into massive haulers. These trucks are capable of hauling 320 tons, or about 6 whales, and are about the same size as an average 2-story house. These huge hauling machines carry the blasted rock, which contains minerals called ore, out of the mine and drop it into one of the world's largest rock crushers. This giant crusher turns the big car-sized chunks of loose ore into more manageable, basketball-sized rocks at the rate of about 10,000 tons per hour, and then drops the crushed ore onto a conveyor belt. The conveyor system, which is basically a giant moving sidewalk for rocks, carries the ore through a 3-mile tunnel, then continues up hills, down hills, and past 6 transfer stations until it reaches the Kennecott grinding facility. This 5-mile trip takes about 29 minutes. If only rocks could appreciate the fun of traveling 5 miles on a moving sidewalk. When it reaches the grinding facility, the ore runs through a series of giant rotating mills. This grinds the basketball-sized rocks into a fine powder. After all that blasting, hauling, crushing, conveying, and grinding, the copper is finally ready to be separated from all the other minerals and materials that surround it. This is also where the process switches from brute force to applied chemistry. The finely ground ore is poured into flotation cells and mixed with exactly the right amounts of water, air, and chemicals. This causes all of the copper-bearing minerals to cling to air bubbles and take a free ride to the top of the flotation cell. The result is a liquid material called copper concentrate, which is now about 28% pure copper. This concentrate is pumped 17 miles through a long pipe to a filtering facility and dumped into a big storage tank. At the filtering plant, the concentrate is pressed, filtered, and dried in a massive rotating dryer. After it's done, the material looks a lot like coffee grounds. This powder goes into a large, very hot flash furnace, which causes the dried concentrate to melt and turn into a molten metal called matte copper. During this process, sulfur gases burn off and are then captured and cleaned. A combination of iron and silica rises to the top, and the heavier copper matte sinks to the bottom. This matte, which is now about 70% pure copper, is collected, cooled, and sent through yet another series of furnaces. This burns off most of the remaining impurities and leaves us with molten copper that's about 99% pure. This nearly pure copper is poured into 700-pound copper plates called anodes and left to cool. 99% pure copper is good, but getting to 99.99% takes a little extra molecular mojo. The anodes are shipped to a final tank house facility, where they're sandwiched between stainless steel plates and loaded into big square tanks that are designed to conduct electricity. The tanks are filled with an electrolytic solution that creates positive and negative electrical currents, just like the world's biggest car battery. This current causes the pure copper ions to jump to the stainless steel plates. It's a pretty strong attraction. The result is a 99.99% pure copper cathode. These cathodes are stripped away from the stainless steel plates, corrugated, strapped together into 5,000-pound bundles, and whisked away to their final destinations. And finally, they're turned into cell phones, computer components, copper pipes, copper wire, and many other things that make our modern lives possible. That's the amazing story of how we take copper from this to this. 99.99% pure copper. It's not easy, but when you stop and think about what our lives would be like without copper, it's worth it.
All right, so that is how copper are being extracted from its ore. So we have used a lot of copper in our life with or without us realizing it. So we are depending on copper. So copper is actually the first metal that is one of the first metal that's being used by human civilization. So we even have historian has used the civilization named after copper, Bronze Age. So that is a type of copper alloy. So the general properties of unalloyed copper is that it is soft and ductile, and this is because of the FCC crystal structure. So it also has almost unlimited capacity to be co-worked. So if we want to strengthen them, copper alloy can be unalloyed copper can be co-worked. So we can shape them to any shape because of that FCC crystal structure. And also unalloyed copper is highly resistant to corrosion in diverse environment, in seawater, in our ambient atmosphere, and also in some industrial chemical. So that's why copper is used in a lot of marine application because of this resistant to corrosion. So one of the main application of unalloyed copper is that it is being used in as electrical to transmit electrical power. This is because it has high electrical conductivity. Again, why is this? Is because it has only one valence electron. So copper, if you go and do your research, can have one or two valence electron because of the D and also the D and P shell, SPD, D and the F shell. So you can have a look at that. So some copper, if you are interested, but at your level, you don't need that. But because of this one valence electron, the energy, as we know that the energy for this this valence electron needed in order for us to free them from the shell, it depends on the number of the number of electron there. So the lower the number of the electron on the outer shell, the easy for it to be free. So the freedom is easy because copper only have one valence electron. So they have been used in the production of wire, rod, and plate in a lot of engineering application. So one of the most common classification of copper alloy is brass. So when we combine copper with the major alloying element as zinc, we call them as brass. So the copper zinc brass consists of addition of 5 to 40% of zinc. So we've learned this in module 6. So when we have the amount of 5 to 40% of zinc, we classify this as brass. So up to 35% of zinc, we will have alpha solid solution in our crystal structure. So we will have a crystal structure of copper with zinc residing inside the crystal structure. But when we have more than that, up to 40%, we will have another phase that will exist in the microstructure, and this is the beta phase. So the alpha in the final microstructure, we will have both alpha and beta. So you can see that because of this, so when we have a 40%, for example, it is in this region. So what will happen is that we will have a microstructure consists of alpha and beta, alpha and beta in the microstructure. So that what will happen is that we will have two phases. These materials will be stronger, but at the same time will be less ductile if we compare to this one. So that's the difference between the brass alloy that has different composition. So the effect of sometimes we add, instead of we just have zinc, we add other alloying elements. So we have the major alloying element as zinc, but we added different alloying element as to improve different properties in these materials. So these here listed, we can add aluminum, lead, zinc, magnesium, aluminum, magnesium, lead, nickel, phosphorus, tin, arsenic, silicon, and also iron as the third alloying element. What will happen is that we will improve its property, its different properties. So for example, here, if we add aluminum, it will increase the overall strength and also reduce the ductility of the copper zinc, the brass alloy. So you must imagine this is considered like the third alloying element. And also if we have added nickel, for example, so nickel has a very good corrosion resistant, chemical resistant, and wear resistant as well. So if we add nickel into brass, it will improve that properties. So you can read through this alloying element, the effect of the alloying element, to see what's the difference between them. These are some of the applications that use copper. So for architectural purpose, we seen a lot of copper alloys being used as well. And normally for architectural purpose, it's decorative because copper has that color, the copper color, it is quite pleasing to our eyes. So we use copper for that purpose. And also plumbing, we use a lot of copper plumbing as well, brass plumbing. Musical instruments, we use copper as well, and also for these other decorative purposes. So we use a lot of brass in our application. For marine application, as I have explained, we have used a lot of copper alloy, brass alloy as well. So copper alloys such as brass are traditionally used in marine engineering for heat exchanger tube. This is because they are resistant in the seawater application. So when we use it in the in marine application, they can resist corrosion. So they can last longer. All right, so that's for brass, and then we have bronze. Bronze is another type of copper alloy that has been used extensively in engineering application as well. So when we call bronze, alloy that we call bronze is normally when we have tin as the major alloying element. So bronze with 1 to 2% of tin is going to solidify in a solid solution alloy. So we have one type of phase in the final microstructure. So as you can see here, when we have 1 to 12, we have alloy that exists in this alpha solid solution. So when we, especially, but when we, for example, this one, at a certain temperature, precipitates of epsilon will start to see. So what we need to do is actually we need to quench them to retain it into that alpha solid solution. Okay, so that's for the bronze with 1 to 2% of tin. So we can also add other alloying elements such as arsenic, phosphorus, aluminum, manganese, and silicon to have different properties. So bronze, because of that alpha bronze, because of the FCC crystal structure of copper, it is quite ductile, and upon exposure to air, bronze oxidizes. So what will happen is that it will create a green layer outside that outside the surface that is been exposed to air, to create a green layer that we call as patina. So the Statue of Liberty is actually made of, it is made of different metal at the base, but it is being clad with bronze at the outside to protect the middle part of that statue. So the bronze layer on the outside that you see as green color, if they polish it, you can actually see the bronze original color. So that green layer is what we call as patina, and it protects the layer of bronze underneath it. But there is a law in the United States that you cannot polish that green color. So it's actually prohibited to be polished. So that green color is actually the green layer, oxide layer of the bronze alloy. So these are some of the applications of bronze alloy. So it is made, a lot of bronze bearings are made of these materials, reduction gear, and also for pump fitting. But as you can see from the production of copper, it is quite an expensive materials. So it's actually used in a very high performance and quite expensive application. So for example, watches, the expensive watches, the gears inside are actually made of, some of them are made of copper, some of them are made of bronze. Okay, so just a fun fact here for the bronze, the bell, the large bells that they use in the temple, in the church, mostly are made of bronze. So for example, this is a bell of King Seong-deok in Pohang, South Korea. So this alloy, these bells are made of bronze. So it takes about 30 years for this bronze to be made. So the first cast that they made, they use bronze with 22% of tin inside these materials. So what happened is that they use the first one, they use a lot of tin. So what happened was that it becomes too brittle. So when they cast it, it breaks. So the second one, they use the 22 to 24% of copper. So it is around that alloy. Okay, so as you can see that. But what happened was that when it solidified, as you can see, when it solidified, it comes from this, you have alpha, and then you start have alpha, beta here. But eventually you will have alpha, and also here you can see alpha and delta. So this delta is quite brittle. And if you solidify them in equilibrium, eventually you will have alpha. and epsilon. Again, this is quite brittle. So when they strike that alloy, they don't have the sound that they want. So it must have the sound of like from the distance, it's like a crying baby. That's what the monk want. So I don't know if this story is correct or not, but that's what the history that was written. Okay. So the third one, the monk said, we must sacrifice a baby into the molten metal. So I don't know if this is true or not. Okay. That's what they did. But actually what happened was that when it reached to this composition, they used the same composition and they reached to this temperature, about 600 degrees Celsius, they quench it. So when they quench it to a room temperature, they will prohibit all the other phases from precipitating or from transformation. So in the end, they will have alpha and beta solid solution. And when they strike it, they get the correct sound that they want, the sound like a crying baby. So most of the bronze metal that you see all around the world are made of this type of alloy, the bronze with a composition around this composition of copper and of tin. All right, and then we have a new generation of copper alloy, which is copper beryllium. So this is produced with around 0.6 to 0.2% of beryllium and also some percentage of cobalt. So this alloy can be precipitated, can go precipitation hardening heat treatment process. So what will, as you can see here, this final product, if this is cool in equilibrium, you will have a microstructure that looks like this, alpha, 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 with gamma at the precipitates out of the grain boundary. So through precipitation hardening, we can increase the temperature again to when all the beryllium being saturated inside alpha, and we need to quench them and do age hardening. So what will happen is that gamma instead will come out in the matrix of the alpha as a very fine particle of precipitates. So this type of copper alloy can be heat treated. And some of the application, because of its good strength and also high stiffness, and also possess corrosion resistance and fatigue properties, they are useful in applications where applications such as spring gears and also for valves. So in a commercial aircraft, the landing gear, bushing and bearing are made of copper beryllium. All right, so another properties of copper and its alloy, it has the antimicrobial properties. So what happens is that if we sneeze on top of copper alloy, that bacteria, if we touch it with, if our hand have bacteria or virus like COVID, they can die when they land on copper surface. So that's why a lot of, especially overseas, a lot of the surface that needs a lot of touching are made of copper alloy. So the reason why is that when this bacteria land on copper surface, what's going to happen is that copper surface will release the copper ion. So copper ion is electrically charged. So we learn ion, the anion, and also the cation. So what happened was that copper ion is an electrically charged particle. So one microbe is transferred by touching and sneezing or even vomiting, land on the copper surface. This ion will prevent the respiration, and also it will punch a hole on the bacteria cell's membrane, and this will destroy the DNA and also the RNA inside that virus or the bacteria. So that is another excellent properties that I thought that it's interesting if you want to know for copper alloy. All right, so that's it for today. So today, in summary, we have learned about non-ferrous metal and how they can be classified as either wrought or cast alloy, and the alloys that are amendable to forming by deformation, we call them as wrought alloy, and the one that is brittle, because of the amount of alloying element is much higher, it can only be fabricated by casting process. So we classify them as cast alloy. And aluminum and copper can also be alloyed with other alloying element to improve their properties. So that's it for today. We will continue our discussion on non-ferrous metal in the next lesson, where I will talk about this alloy, titanium, nickel, also magnesium, and where we use them. All right. So as for today, apart from Hang Yi just then, who asked me, who asked? Apart from that questions that I will come back with you. Hang Yi is my solid student.
It is asking,
yeah. What's your name again? You always ask me questions. Chin. All right. Chin. Okay, I will try to remember. Chin.
Thank you, Doctor.
All right. Also, I would like to ask. One student have asked me. I have asked answer my question in the first few week, and I promised to give him 2 marks, but now I forgot who is he, because the name is in my office and I don't have that book with me. Is it Chen? There's one student. If you remember who you are, let me know, because I remember I promised you 2 free marks for answering my question. Yes, Chen Jiong Heng. All right. Okay, so I will give you extra 2 marks for your test. All right. Any other question for today? I will post this video so you can watch this again if you're interested in watching it and looking at my face. All right, guys. Kalau tak ada soalan, I'll leave you for you to. There's no more tutorial after this. It's all just application. So I'll just.
Doctor, will we have homework?
Yeah, there will be one more homework.
Oh, one more. Okay.
Yeah. I will give you homework on non-metallic materials.
After the test lah.
Yalah. Okay, before exam. Before
Takut
exam
ni.
you submit. Okay.
Kalau lepas before test ni susah lagi. Banyak test lagi, Doctor.
I'll try after exam. Okay.
Thank you, Doctor.
I will give you questions earlier, but you submit after test.
Okay, understand. Thank you, Doctor.
All right, no problem. Kelas saya chill sahajalah. Nak hantar lambat, just inform me and I will change the date. Don't worry. Kita pun MCO, no stress. Okay? We have enough stress already. So have a check on your Turnitin. If you cannot see your answer there, you cannot see your submission, let me know. I will contact the librarian and ask them to retrieve your answer. And if they cannot retrieve, I will just ask you to submit it again to me privately. All right. So if there's no question, ada soalan lagi tak? Syafi tak ada suara hari ni. Zulhilmi, adakah Zulhilmi hari ni? Zulhilmi, I can see.
Yeah.
Okay. Faham tak hari ni kita buat apa? What we
Faham,
learned today? Okay. Alright. Izzah ada, Connie ada. Hi Connie. Connie tak pernah dengar suara dia tapi sampai pernah dia message saya. Alright lah guys. I'll leave you. Enjoy your afternoon. Go do something else. Don't worry about material science. For this topic and next topic, we will watch a few more videos. Okay? I'll see you guys on Wednesday.
Okay. Thank you, Dr.
You're welcome. Assalamualaikum. Selamat petang semua.
Waalaikumsalam. Thank you, Dr.
You're welcome.
Thank you, Dad.
Welcome.